earlier I have introduced the concept of random variables. So, the concept of random variable is defined in the way that it is a real valued function on the sample space. And that means, we are interested in a single characteristic which is reflected from the sample space, single property or one value we want to take. But many times from the random experiment we want to extract more values. Suppose we are considering certain examination and we are looking at marks of a student, then we may be looking at the marks of the student in say 5 different subjects. So, marks in 5 papers. So, it could be like x 1, x 2, x 3, x 4 and x 5. If a patient goes to a doctor and a doctor takes certain measurements on him, for example, the doctor may ask his age, the doctor will take his weight, the doctor may record his say blood pressure. So, we may write say for example, x 1 as the weight, age, x 2 as the weight, x 3 as the blood pressure, or we may also look at say his sugar level, his pulse rate, maybe his height also. In that case, from the single random experiment we are extracting 6 dimensional vector. So, in general we say that x 1, x 2, x n is a random vector. Let me denote it by x, random vector. Then x is actually a function from omega into r k, and we keep the condition of measurability, that it is a measurable function. Now, like in the case of random variable, we may have a discrete or continuous random vector. We may also have in various type of cases. For example, when we are recording age may be recorded in the rounded of years. In that case, it will be a discrete random variable. Weight may be recorded as a continuous variable, blood pressure, sugar level, etcetera, may be recorded as the say continuous variables. So, it could be that some components of the random vector are discrete, some components are continuous, or all of the components are discrete and all the components are continuous. So, in that case the distribution of the random vector is described differently. Let us take 2 special cases. One is when all the components are discrete, and second one when all the components are continuous. So, we consider a discrete random vector, say x is equal to, now I will restrict my attention to 2 dimension, n is equal to 2, let us consider. So, x y say. So, this is also called bivariate random variable. So, if we are saying it is a discrete, we can consider the probability mass function of x y is described by p x y x I y j, that is equal to probability x is equal to x I and y is equal to y j for x I y j values belonging to some space of values of in x cross y. We have 2 conditions. One condition is that p x I y j is greater than or equal to 0, and second condition is that when we sum over all the possible values of x I y j in this space, then this is equal to 1. Let me explain through one example here. From a box containing 2 defective, 3 partially defective and 3 good fuses, a random sample of 4 fuses is selected. Now, let us consider x is the number of defective fuses in the sample and y is the number of partially defective fuses in the sample. We want the distribution of x y. What is the distribution of x y? So, we assume that all the selections are equally likely. In that case, we can evaluate this probability distribution in the following fashion. First of all, what are the possible values that x and y can take? Since there are maximum 2 defectives, x can take values 0, 1 and 2 and y can take values 0, 1, 2, 3. And let us consider what is the probability that x is equal to say 0, y is equal to 0. Now, so this is actually p x y 0 0. Since the maximum number of good fuses is 3 and we are selecting 4 fuses, therefore, at least one will be either defective or partially defective. It is not possible that all of them are good, because x is equal to 0, y is equal to 0 corresponds to the case when all the fuses which have been selected in the sample are good, but that is not possible. So, this probability is 0. Let us consider another one, probability that x is equal to 1, y is equal to 0. In notational form, we will write it as p x y 1 0. Now, this means that out of our selection, from 2 defectives, 1 has been selected and from partially defective none are selected and all other good ones are selected. So, basically it is like 3 C 0 and 3 C 3 divided by 8 C 4. So, we can simplify this, this turns out to be 1 by 35 or we may write it as 2 by 70. If we consider say probability x is equal to 0, y is equal to 1, that is p x y 0 1, then this turns out to be 2 C 0, 3 C 1, 3 C 3 divided by 8 C 4 and this value can be evaluated as 3 by 70. Now, likewise we can calculate all other terms, that is p x y for x taking values 0, 1, 2, y taking value 0, 1, 2, 3. This p x y can be calculated. We can represent it in a tabular form like on this side we can show the values of x, on this side values of y 0, 1, 2, 0, 1, 2, 3. So, this table will represent the probability distribution of x y. So, this is 0, p 0 1 we have calculated, it is 3 by 70, p 1 0 we have calculated, that is equal to 2 by 70 and in a similar way other values can be calculated. I am substituting these values 9 by 70, 3 by 70, 18 by 70, 18 by 70, 2 by 70 and then you have 3 by 70, 9 by 70 and 3 by 70 and 0, because x is equal to 0, y is equal to x is equal to 2 and y is equal to 3 is not possible, because total number of selections is only 4. Now, we also introduce the concept of marginal and conditional distributions. So, marginal distribution of x is defined as p x x as the summation over all the values of y. Similarly, the marginal distribution of y, that is defined as p y y, if we sum over all the values of x. We can also define. So, in this particular case, for example, the marginal distribution of x p x x, it is obtained by summing the probability distribution of x y over y. So, p probability x equal to 0, that is obtained by summing over y is equal to 0, y is equal to 1 and y is equal to 2 and y is equal to 3. So, that is equal to 15 by 70, 40 by 70 and 3 plus 9 plus 3, that is equal to 15 by 70. So, this rightmost column gives the marginal distribution of x. Similarly, if we add with respect to x, we get the marginal distribution of y. For example, if we add the first column, we get the probability of y is equal to 0. So, this is equal to 5 by 70. If we add the values in the second column, we get 30 by 70. If we add in the column corresponding to y is equal to 2, we get 30 by 70, and if we add in the column corresponding to y is equal to 3, we get 5 by 70. So, this is denoting the marginal distribution of y. We can also talk about the conditional distributions. Conditional probability mass function of x given y is equal to y, that is defined by p x y is equal to say y j, x I given y j, that is equal to the joint distribution of x I y j, x and y divided by the marginal distribution of y at the point y j. Similarly, we can define conditional distribution of y given x is equal to x I say, that is p y x is equal to x I y j, that is equal to p x y p x x I. So, once we are having the conditional and the marginal distributions, we can answer any questions regarding the probabilities of x, y, x given y or the joint distributions of x and y. For example, what is the probability here? Say we want to find out what is the probability that x plus y is equal to 2. Then this is equal to probability of x y is equal to say 0 2 plus probability x y is equal to 2 0 plus probability x y is equal to 1 1. So, that is equal to 0 2 probability is given by 9 by 70, probability of x equal to 2 y is equal to 0, that is given by 3 by 70, and probability of x equal to 1 y is equal to 1 is given by 18 by 70, that is equal to 30 by 70 or 3 by 7. We can answer any question regarding say y. What is the probability say that y is greater than or equal to 2? Then it is equal to probability of y is equal to 2 plus probability of y is equal to 3, that is equal to 30 by 70 plus 5 by 70, that is equal to half. Similarly, suppose I want to answer what is the question regarding x is equal to 1 given y is equal to 2. So, this is equal to probability 1 2 divided by probability of y is equal to 2. Now, P 1 2 that is equal to 18 by 70 divided by probability of y is equal to 2, that is equal to 30 by 70. So, that is equal to 3 by 5. We can answer probability statements regarding the joint, marginal and conditional distributions. Now, let me also define the probability density function for a continuous random variable, bivariate continuous random variable. So, let us consider x y a bivariate continuous random variable, say, and the probability density function, it is called the joint probability density function of x y. So, this will satisfy the properties that f x y has to be greater than or equal to 0 for all x y. The integral over the whole region over R 2 of f x y must be 1. Of course, here the order of integration is not important, whether we do dx dy or dy dx, both should give the same answer. And for any set, say A in R 2, of course, this should be a measurable set. Probability that x y belong to A is given by the integral of the joint density over the region A. Let me explain through one example. Let us consider, say, f x y is equal to x plus y for x between 0 to 1, y between 0 to 1. Suppose I want to calculate what is the probability of x plus y less than 1. Then let us determine the region in the 2-dimensional space. Here x and y both are lying between 0 to 1. And when we are saying x plus y is less than 1, then this region is so the region of integration then becomes, for x it is from 0 to 1 minus y, this line is x plus y is equal to 1, and for y it will be from 0 to 1. So, one can easily evaluate this integral, this value turns out to be 1 by 3. Like in the case of discrete random variable, here also we can define the marginal and conditional distributions. For example, marginal probability density function of x is given by integrating the joint distribution with respect to y over the appropriate region. Similarly, the marginal distribution of y, that is given by f y y, is equal to integral of the joint density with respect to x over the given region. For example, in this particular case f x x, in this case this will be equal to integral of x plus y dy from 0 to 1, that is give us x plus half. Similarly, if we consider, say, here f y, that will be y plus half for 0 less than y less than 1 and 0 elsewhere. We can also talk about the conditional densities, conditional probability density function of x given y is equal to y. So, that is defined by f x given y is equal to y it is equal to the joint distribution of x y divided by the marginal distribution of y. In a similar way, we can talk about the conditional probability density function of y given x. That is equal to the joint distribution of x y divided by the marginal distribution of x. For example, in this case, this value will turn out to be, the joint distribution is equal to x plus y divided by the marginal of y, that is y plus half for 0 less than x less than 1, and here y is any value fixed between 0 and 1. Suppose I say find the conditional probability, say probability that say x lies between 0 to half, given that y is equal to half. In that case, I need the conditional probability distribution of x given y is equal to half. So, from here we can substitute the value of y is equal to half, I will get x plus half divided by y plus half. So, now y is equal to half. So, this will become 1. So, the density is simply x plus half, 0 less than x less than 1. So, now if I want the conditional probability here of 0 less than x less than half given y is equal to half, then I will be integrating this density, that is x plus half from 0 to half, that is equal to x square by 2, that will be 1 by 8 plus 1 by 4, that is equal to 3 by 8. So, if we have the joint distribution of x y, we can find out the marginal distributions, we can find out the conditional distributions, and we can answer any probability statement regarding the joint probability, the marginal probabilities of x or y, or the conditional probabilities of x given y or y given x. Now, in the case of univariate random variable, we have introduced the concept of moments. Now, in a similar way, in the case of bivariate random variable also we can talk about moments. We will talk about a slightly more general concept, we call it product moments. So, in general we define expectation of x to the power r, y to the power s. I will use the notation mu prime r s. This is called r sth non-central moment, and it is evaluated by x I to the power r, y j to the power s over all x I y j into the joint probability mass function if x y is discrete, provided this double summation is absolutely convergent. Similarly, if we have continuous, then we can write it as x to the power r, y to the power s, f x y dx dy, and of course, it could be dy dx also, if x y is continuous, provided this bivariate integral is absolutely convergent, provided the series or the integrals are absolutely convergent. In particular, mu 1 1 prime, that is equal to expectation of x into y, that is called the first product moment. We can also define the central product moments. So, mu r s, that is defined as expectation of x minus. So, let me use the notation expectation of x is equal to say mu x and expectation of y is equal to mu y, that is the mean of x and mean of y. In terms of that, we define the expectation of x minus mu x into y minus mu y to the power r, and this is to the power s. This is called r sth central product moment. In particular, if I take r is equal to 1, s is equal to 1, that is called expectation of x minus mu x into y minus mu y, that is defined as covariance between x and y, covariance between x and y. In fact, this has a simplified version also. We can write it as expectation of x y minus mu x mu y, or expectation of x y minus expectation x into expectation of y. Using this, we define Karl Pearson coefficient of correlation between x and y as rho x y, that is defined to be covariance between x y divided by standard deviation of x into standard deviation of y. Now, this correlation coefficient is actually a measure of linear relation. This is a measure of linear relation between x and y, linear relationship. In fact, one can prove that minus 1 less than or equal to rho x y is less than or equal to 1, and rho x y is equal to 1 if and only if x and y are perfectly positively linearly related with probability 1, and equal to minus 1 if and only if x and y are perfectly negatively linearly related with probability 1. Actually, this positive relationship means that x is equal to a y plus b, where a is positive, and negative relationship will mean x is equal to a y plus b is equal to 1, where a is negative. I will explain this concept through calculation in one case. Let us consider, say, f x y is equal to say 6 x y 2 minus x minus y for x between 0 to 1 and y between 0 to 1. Now, for this distribution, let us calculate the covariance and correlation, etc. So, if you look at the marginal distributions f x, that is equal to integral of 6 x y into 2 minus x minus y dy from 0 to 1, then this is simplified to 4 x minus 3 x square for 0 less than x less than 1, 0 elsewhere. And if I look at f y, that is also of the same form because of the symmetry here. So, we can calculate expectation x, expectation y, etc. So, expectation x turns out to be 7 by 12, that is same as expectation y. If we calculate expectation of x square, that is equal to 2 by 5, that is equal to expectation of y square, and if we calculate variance of x, that turns out to be 43 by 720, that is variance of y. We also calculate expectation of x into y, that is equal to double integral 6 x square y square 2 minus x minus y dx dy 0 to 1 0 to 1. So, one can evaluate this, it turns out to be 1 by 3. So, covariance between x y, that is equal to expectation of x y minus expectation x into expectation y, turns out to be minus 1 by 144, and therefore, the coefficient of correlation, that turns out to be, that is covariance of x y divided by square root of variance of x into square root of variance of y, that turns out to be minus 1 by 144 divided by 43 by 720, that is equal to minus 5 by 43, which is a very low negative value. So, if x y are, if rho x y is equal to 0, we say that x and y are uncorrelated. Now, there is a related concept, that is of independence. We say x and y are independently distributed random variables if the joint probability mass function is equal to the product of the marginal probability mass functions, and similarly when we are considering the continuous case, it should be the joint probability density function is equal to the product of the marginal probability density functions. For example, let us take f x y is equal to say 4 x y e to the power minus x square plus y square, x is positive, y is positive, it is equal to 0 elsewhere. Let us look at say f x y, f x. So, here I will integrate with respect to y from 0 to infinity. Now, if you look at the term y e to the power minus y square, it will have integral e to the power minus y square by 2. So, at infinity it will become 0, at 0 it will become 1. So, you will get twice x e to the power minus x square for x greater than 0. Similarly, if I look at f y, then that will turn out to be 2 y e to the power minus y square. So, note here that if I multiply f x and f y, I will get f x y. Therefore, x and y are independent here. Now, like in the case of univariate, one can talk about joint moment generating function of x y as m x y s t, that is equal to expectation of e to the power s t s x plus t y. Notice here that if I put t equal to 0, then I will get the moment generating function of s, and if I put s is equal to 0, then I will get the moment generating function of y. We have powerful results connecting the independence to the moment generating function. We have the following theorem: x and y are independent. This implies and implied by the joint MGF is equal to the product of marginal MGFs. We have another consequence also, that if the random variables are independent, if x and y are independent, then the moment generating function of the sum is equal to the product of the individual moment generating functions. In fact, this is the one which is used to prove the additive properties of various distributions, like I gave the example of binomial distribution additive, geometric distribution adds up to the negative binomial distribution, exponential distribution adds up to the gamma distribution, the linearity property of the normal distribution, etcetera. All of those things were proved using the moment generating function approach only. Now, using the moment generating functions, if the random variables are independent, one can find out the distributions of the sum, but many times we may be interested in the distribution of functions of random variables. Distributions of functions of random variables. For example, I have x y and I define u is equal to say g 1 of x y and v is equal to say g 2 of x y. So, if g 1 g 2 is a measurable function, then u v is also a random vector, and one can find out the distribution of u and v. I am not going to discuss in detail the distribution here. Like in the case of one variable, when we had the x as a discrete random variable and g x was also discrete, there was a direct way of obtaining the distribution of g. However, if the distributions were continuous, in that case we had a differential formula, that means we had f x written at g inverse y and then we multiplied by d g inverse y by dy, or you can say dx by dy. When you are dealing with more than one variable, then that d term is represented or replaced by a Jacobian term. I will state it in the form of the following theorem. So, Jacobian approach for finding density functions of joint random variables. Let x is equal to x 1, x 2, x n be a continuous random vector with joint probability density function, say f x. Here x is denoting the vector here x 1, x 2, x n, and let us define u I is equal to g I of x for I is equal to 1 to n, and this u is equal to u 1, u 2, u n. It is a 1 to 1 mapping from R n to R n. And we also have the inverse transformation, say x I is equal to h I of u for I is equal to 1 to n. Let these be the inverse transformations. And if the partial derivatives del x I over del u j exist, and we define the Jacobian of the transformation as del x 1 by del u 1, del x 1 by del u 2 and so on, del x 1 by del u n and so on, del x n by del u 1 and so on, del x n by del u n. And we assume that this is non-zero over the range of the transformation. In that case, the joint PDF of u is equal to u 1, u 2, u n is given by f u u, that is equal to f of, now x i's are replaced by h 1 of u and so on, h n of u multiplied by the Jacobian, the absolute value of the Jacobian. For example, let us consider, say, let x and y be independent uniform 0 1 random variables. Okay. That means, the joint distribution of this is given by 1, 0 less than x less than 1, 0 less than y less than 1 and 0 elsewhere. Let us define, say, u is equal to x plus y and v is equal to x minus y. Then if you see this, you can find out the inverse transformation, x is equal to u plus v by 2, y is equal to u minus v by 2. So, if I look at the Jacobian, the derivatives of del x by del u is half, del x by del v is half, del y by del u is half, del y by del v is minus half. So, this is equal to minus half. So, modulus of Jacobian is equal to half. So, the joint distribution of u v then is equal to half, 0 less than u plus v less than 2, 0 less than u minus v is less than 2, and of course, if you write down the absolute regions of u and v, u is from 0 to 2 and v is from minus 1 to 1 and 0 elsewhere. So, this is the joint probability density function of u v. I introduce the concept of sampling distributions now. So, firstly, let us consider, say, x 1, x 2 and so on be a sequence of independent and identically distributed random variables with mean mu and variance sigma square. Let us use the notation x n bar is equal to 1 by n sigma x I. Since it is a sequence, if I consider the first n of these observations, I take the mean as x n bar. Then the distribution of root n x n bar minus mu by sigma converges to normal 0 1 as n tends to infinity. Now, this is a very powerful statement. I am considering x I to be sequence of any independent and identically distributed random variables, but mean is mu and variance sigma square is given to us. Then the distribution of the sample mean, that is x n bar, is approximately normal. So, this famous result is known as the central limit theorem. This result has further generalizations. For example, we may have independent, but non identically distributed random variables, or we may not even have independent random variables. So, then under certain conditions, the distribution of the sample mean or the sample sum still can be approximated by a standard normal distribution. So, this is one of the first results in the case of sampling distribution. What do you mean by sampling distribution? If we are considering several observations from the same population or with the same distribution, then if I consider any characteristic of that, for example, mean, variance, etc., the distribution of that is known as the sampling distribution. So, we can say normal distribution itself is a sampling distribution. We define some more sampling distributions. One is the well known chi-square distribution or chi-square distribution. Let x 1, x 2, x n be independent normal 0 1 random variables, and let us define w is equal to sigma x I square, I is equal to 1 to n. Then the distribution of w is said to be a chi-square distribution on n degrees of freedom. N degrees of freedom, that term is used here, and we use the notation w follows chi square n. So, one can actually derive this distribution, because I can derive the distribution of x 1 square from normal 0 1, x 2 square, x n square, and then we use an additive property to prove this. We can show that each of the x I square follows chi square 1 and chi square is additive. Therefore, sigma x I square will follow chi square n, and actually the density is nothing but a gamma density. The distribution of W is 1 by 2 to the power n by 2 gamma n by 2 e to the power minus W by 2 W to the power n by 2 minus 1, which is actually a gamma distribution with parameter n by 2 and half. But this specific form is known as a sampling distribution because it is arising in a sampling from a normal distribution. In fact, we have a general result that if I consider x 1, x 2, x n a random sample from normal mu sigma square population, and let us consider x bar as the mean and 1 by n minus 1 sigma x I minus x bar whole square as the sample variance. Okay. This is called the sample variance and this is known as the sample mean. Then the result is that x bar and s square are independently distributed. Further, the distribution of x bar, of course, we have seen earlier, it will be normal mu sigma square by n, and the distribution of n minus 1 s square by sigma square, that follows chi square on n minus 1 degrees of freedom. Therefore, when we are doing sampling from a normal distribution, we can answer probability statements regarding the sample mean or the sample variance. We have some properties of W. For example, expectation of W is equal to n, variance of W is equal to 2 n, etc. Since gamma distribution is a positively skewed distribution, chi square distribution will also be a positively skewed distribution. The tables of chi square distribution are given. If this probability is alpha, this point chi square and alpha is tabulated in the tables of a chi square random variable. I will show you here the tables of a chi square distribution, they are given in this particular fashion. So, here you see if this point is chi square alpha on n degrees of freedom, then the probability beyond this on the curve of chi squared probability density function, this probability will be equal to alpha. So, for different values of alpha like 0.995, 0.99, 0.95, 0.05, 0.05 etcetera, 0.25 etcetera, and for different values of n, the points chi square and alpha are tabulated here. We talk about some further sampling distribution. Another one is called the famous student's T distribution. Let x and y be independent random variables. Let x follow normal 0 1 and y follow chi square n, and let us define t is equal to x divided by root y by n, that we can write as x into root n by y. Then this is said to have T distribution on n degrees of freedom. The probability density function of T is obtained as one by root n beta n by 2 half 1 by 1 plus t square by n to the power n plus 1 by 2, where t lies between minus infinity to infinity. As you can see, this is a symmetric distribution around t is equal to 0. The mean of this will be 0, and the variance of this is n by n minus 2, which is valid for n greater than 2. As n tends to infinity, the probability density function of t converges to phi t, that is the probability density function of normal 0 1 random variable. Therefore, for large values of n, for n greater than or equal to 30, the approximation is very good. Once again, on the curve of t distribution, suppose I consider this probability to be equal to alpha, then values of t and alpha, that is the point beyond which the probability is alpha, then these values are tabulated in the tables of t distribution in this particular fashion. So, this point is t and alpha, the probability beyond this is alpha. So, for different values of alpha like 0.005, 0.01, 0.025, 0.05 etcetera, and for different values of the n degrees of freedom, the points t and alpha are tabulated here. If I consider say x1, x2, xn from normal mu sigma square, and we define x bar. So, x bar minus mu by s, then this we can write as square root n this. So, this we can write as, because we have seen that x bar minus mu by sigma into root n, that will follow normal 0 1, and we are having n minus 1 s square by sigma square following chi square on n minus 1 degrees of freedom. So, if I write this as root n x bar minus mu by sigma divided by square root of n minus 1 s square by sigma square into n minus 1, then this is same, this will follow t distribution on n minus 1 degrees of freedom. Therefore, this is also a sampling distribution. Then we also consider f distribution. Let x and y be independent, and x follows say chi square on m degrees of freedom and y follows chi square on n degrees of freedom. Then x by m divided by y by n, that is equal to n x by m y. This is said to follow f distribution on m n degrees of freedom. That is, we write this, let me use the notation say v, v follows f on m n degrees of freedom. The probability density function of f can also be derived, that is equal to m by n to the power m by 2 divided by beta m by 2 n by 2 v to the power m by 2 minus 1 1 plus m by n v to the power minus m plus n by 2, where v is positive. The mean of this is equal to n by n minus 2, the variance is equal to twice n square into m plus n minus 2 divided by m into n minus 2 square into n minus 4. This is of course valid for n greater than 4, this is valid for n greater than 2. We can actually see that it is a sampling distribution. If we consider say a random sample x1, x2, xm from say normal mu 1 sigma 1 square and say y 1 y 2 y n is another random sample from normal mu 2 sigma 2 square, and suppose these samples are considered independent. Let us define say S x square as 1 by m minus 1 sigma x I minus x bar square and S y square as say 1 by n minus 1 sigma y j minus y bar whole square. Then m minus 1 S x square by sigma 1 square, this follows chi square distribution on m minus 1 degrees of freedom, and n minus 1 S y square by sigma 2 square follows chi square on n minus 1 degrees of freedom. So, if I take the ratio, if the samples are independent, then these two variables are going to be independent, these two are independent. So, if I consider the ratio m minus 1 S x square by sigma 1 square into m minus 1 divided by n minus 1 S y square by sigma 2 square into n minus 1, that is equal to sigma 2 square by sigma 1 square S x by S y square, that will follow f distribution on m minus 1 n minus 1 degrees of freedom. So, f distribution is a sampling distribution. As you can see, this is a positively skewed distribution. Of course, the level of skewness will depend upon the parameters m and n here, and if I consider f distribution and this probability is alpha, then this point is called f m n alpha. The tables of f m n alpha are tabulated for selected values of alpha and selected values of m and n. For example, you can see here this is corresponding to alpha is equal to 0.1. On this side m is varying and on this side n is varying, and for these values f m n values are f alpha m n values are tabulated. This is for alpha is equal to 0.1, and similarly for alpha is equal to 0.05 also these tables are given. So, most of the statistical tables contain the tables of f variable. There is a relation of f in the terms of reciprocal, because if I take the reciprocal of f variable, then also we get an f distribution. So, actually if I say f m n 1 by that, then this is equal to f n m, and therefore, if we consider the point f of 1 minus alpha m n, that is equal to 1 by f alpha n m. So, these are some of the sampling distributions, and they are used for inference problems, particularly to find out the confidence intervals and testing of hypothesis problems. In the next lecture, I will be introducing the problem of inference, in particular the problem of point estimation.